Lightweight, portable, innovative. TESCO's 6330 meter site analyzer is the most versatile and complete tool for testing the entire functionality of transformer-rated metering installations. Contact us today for a free demo.
Well, thanks everybody. We really appreciate you spending some time with us. These are becoming popular events that we put together, and we really want to encourage anybody out there to let us know what else we can cover, what other things can we talk about that would interest you. I think that's it's a good concept. It's the world we live in right now, so we'll move ahead and start this presentation. It should be probably 45 minutes or so, and then questions. And feel free to ask a question with Andy. I'm restricted a little bit. I got the screen up on my side. Can I just check, Andy? You can see that site testing and verification.
Yes.
Okay. All right. Good. So is everything okay at your end?
Looks fantastic.
Good. Okay, dokie. All right. Well, thanks again. This particular session we're going to do is more to do with meter site testing and verification, which is really covering a whole range of different and testing procedures that we've done over the years. This particular one we're proud of because this one incorporates a new product that we've introduced, which we're excited about, and it's a venture into doing field site testing as opposed to doing laboratory and bench testing. So it contains quite a bit of information in here. We've cut it down a little bit for time period, but we can always expand on that if anyone wants any more details later on. Okay, so my name is John Carroll. I work with TESCO. I'm the Western Regional Sales Manager, and introduced everybody there. So welcome again. Let's go ahead and start the presentation. So some of the topics we wanted to cover today, really wide varied, but the transformer-rated meter forms themselves. We're going to focus mainly on transformer-rated customers. That's the real key to this type of testing. Residential testing can be done in lots of different ways, and we cover those very successfully. But this is a particular type of test where we're really not going to interfere with the customer service. We're trying to do as much testing as possible without that. So it's an in-service test. We'll talk a little bit about test switches and current transformers themselves. We'll talk a little about site inspection and safety checks. A vital part of this whole procedure is the fact that we are exposing ourselves to energized circuits here. As you can see from that picture, there's an energized circuit with the cover open. These are all conditions that the field is very experienced with. A lot of meter technicians, journeyman linemen, they're all trained very well in this environment. So I don't think it's any surprise to anybody, but it doesn't do any harm to cover it a little bit more to remind ourselves. Metering accuracy is something critical in this course, and that's the main focus of what we're going to do today. And checking the health of your CTs and PTs. These devices, for the most part, are not really viewed very often. I mean, nobody can really see them. People who walk up to any kind of site like this will just see these gray boxes with cables everywhere and possibly the meter. That's about the only recognized piece of equipment. But underneath that, as we can see, there is a lot going on. And all of that is a vital component to doing the overall testing. When we do this, we're also doing a site verification. And that's really why we're making that point. It's site verification, not just meter testing. We will also have a little discussion about demagnetization and admittance. These are two particular types of tests that are also been recognized over the years. And this is something else that we want to cover. And then we'll finish off with a little bit of harmonics determination and effects. It's a topic I've been used to dealing with for many years. It's been around for many years. It sort of ebbs and flows a little depending on conditions, and we'll talk a little bit about the effect of harmonics themselves. So with that, we'll move forward a little bit. So let's talk about transformer-rated metering. Metering really measures and scaled down representation of the load. And a little pictorial representation of a factory here is given as an indication of the meter itself and the CTs and the service drop. So really what we're doing is we're scaling it down. And we're scaling it down in order to make it safe to work on. And all of this is done through CTs and also VTs, which are voltage transformers, sometimes called VTs. And all of this is done obviously with accuracy in mind. So that's why we mentioned multiple times through this presentation that the CTs themselves are a vital part of this testing circuit. If anything happens at that CT position, it's likely to affect the metering accuracy or the metering, not so much the accuracy perhaps, but certainly it's going to affect the incoming current, which is going to be part of the overall measurement. So the meter in this case is not really part of the circuit, so it can be removed fairly safely. And we see that quite frequently, and a meter can be tested that way as well, and that's very normal. People do that too. So basic components, most people out there who've dealt with this type of environment before will be familiar with these. These are a typical. There's a lot of this type around. This is a current transformer. In this particular case, we have 3 phases here. It's a 9S installation, so we have 3 of the CTs, in this case 400 amp service, or 400 to 5 is what their ratio is dictated to on their nameplate. And you can see it goes through a test switch, which of course TESCO make very well. So let us know if you need any of those. Shameless plug there for the TESCO test switches. But the idea behind this is really just to give a 5 amp current to the meter, which makes it a safe environment to do operations. And the ratio of that value, which in this case is 80 to 1, is very much the measurement capability here. That's what's going on with the ratio. And that's why we need to measure these on a reasonably regular time. So let's look a little bit at typical metering connections. There's a lot out there. We haven't really focused on all of these. I've just picked 3 of the most common that we tend to come across. I think in the 3-phase world, particularly, the 3-stator transformer rated 3-phase 4YY, which is a 9S at the bottom there. That's the one that's the most likely one to come across with a true 3-phase test. The other forms we see, Form 5, Form 45, Form 6, these are also typical connections for a transformer rated installation. And all of these need to be tested because these are also providing all the input power or input current, which is coming from the actual CTs themselves. So there's a lot going on, a lot of circuits, a lot of connection points, a lot of potential for issues that are going to happen in any of these situations. So metering accuracy. So why are we doing this? Well, we're doing this to verify that that meter, when it's installed in service, is performing accurately. It meets its requirements. It meets its classification accuracy. It meets it under various conditions too. And there's a way of testing those meters very easily. You can remove them, as we said, and you can put them into a test device. We provide a lot of those. And you can run the test and the meter comes back 100% and it's fine. But that's not the whole story. And one of the key components here, of course, as we've mentioned, is the CTs and PTs that are providing the ratio to this, providing the current to it. The problem being, if there's something wrong at that point, the meter, despite the fact that it could be a smart meter, may not necessarily know that. So it's still very accurate, but it's accurately in the wrong way because the current is not where it should be. So there are 2 general ways that we approach this in an in-service situation. And on the right-hand side, you'll see a typical installation where you have the meter itself on the top where the meter socket is. Then you have your test switch. And that test switch obviously allows us to shunt out the CTs and bypass so we can actually energize and look at the signals coming in. But the 2 methods we use, or the 2 methods that are the most common, are under a customer load or what is known as a phantom load. And there's an important distinction between them. The customer load itself is, as I'm put down on this little chart here, is a customer load. It's under billing conditions. It's under the condition of which the multipliers are taken into account. You're not really affecting anything at all other than measuring this. We're not introducing anything. We're not changing anything. We're just measuring what is on site. That is the most real-world condition that you can get. And I certainly, under the years I've been doing this, that is the one that really everybody would strive to achieve every time. Because then there is no ambiguity. You are looking at the billing conditions that the customer has. You're looking at the billing conditions on the day you did this. The issue sometimes is the load itself. The load is obviously the customer's load, which you generally can't determine at the time, other than making an observation on the front, and you can actually determine what's going on. So under a phantom load test, what we do is we shunt out the CTs themselves. We therefore bypass them, and then we drive current into the duct bills, which goes into the meter itself, and we can control that condition. So whilst that's terrific, it doesn't involve the CTs, but it gives you a test. Particularly useful if you have a very low load condition on your customer. I'm thinking of like an irrigation plant or a pumping station where there's seasonal conditions. So therefore, out of season, there's very little going on, so there's very little load. So this is a very significant and foolproof way of doing that test. And we normally do 3 types of testing in this. We do a full load, a light load, and a power factor. We'll talk a little bit more about that later on. Any questions at this point for anybody? Andy, anything specific, or shall I just continue? Okay.
I don't see anything yet, John.
Okay, well, let me know. Just jump in anytime. That's fine.
All right.
So the importance of CT testing in the field that we covered, this is really critical here. You'll see there's a nameplate on there. We'll see one a little bit more detail later on in the presentation, but that's critical too. Make a note of that. I always try and encourage anybody when they go to a site to try and get everyone has a camera phone these days. They're really good. They're high definition on them. You don't have to get too close to the meter itself. You don't have to get too close in the circuit. But you can zoom with your camera and get a really nice close-up of that nameplate. And that nameplate will tell you a whole number of factors under which the accuracy of that CT will be determined. Make a note of it and make sure that the other 2 in the circuit, so there's 3 of them, are the same. I have seen instances where they are not. Don't take it as read that what's on there is actually correct until you've checked it. Well, basically what we're having here is a transformer and a 3-wired circuit. Well, as you can see, if it's wired backwards, you will give a customer a bill of only 1/3 of the actual bill. So that's a 66% reduction. That's significant, even on 1 phase, even with a low current. With 1 broken wire, we might get a customer there who in actual fact has a bill of 2/3 of the actual bill. And remember, this could have been going on since the day they were installed if they were never tested. It's a difficult thing to do at times. We appreciate the safety aspect and we appreciate that there's an energized circuit behind those. But if they're not tested in service, then you really don't know exactly what that meter is receiving. And as you can see, the other issue too is on the nameplate. If there's an incorrect ratio stated on the nameplate, you can get significant changes in your bill. And that's not something anybody really wants. So to continue this, we're looking at cross-phasing. We may have wiring errors. We could have loose and corroded connections. That's highly possible. CTs are mounted backwards. CTs with shorted turns, wrong selections. You can see the list ahead there, and it's not exclusive. There's lots of other things that can happen too. But these are the most common that do happen. And in some cases with these, the concern is that it's not a catastrophic failure we're looking at. So it's not really visible. That's the difficulty with this sometimes, that it's not always a visible condition that you're seeing unless you measure it. So that's why it's also important to keep control over these and have a program where you certainly look at these conditions under these CTs and customers themselves. So let's talk a little about testing at a transformer rated site. I've been doing this quite some time as well, but I'm not a trained meter technician. I absolutely say that right from the get-go, but I've certainly been around them, and it's impressive to me the routine that they go through, almost to the same extent as someone like a pilot. They have a checklist. They go through that checklist. They'll walk around the site. They'll check the conditions. Is there anything obvious? Is there any problem? Is there any vents that have got something in them that is an issue? Is there any studs that are missing? I mean, all list of things. A visual check is vital. They check their PPE, make sure it's correct, make sure they've got the right equipment together. If they can, and they do, in this case, this gentleman was doing this really very carefully and very thoroughly, tightening any loose connections they may have, checking the test switch, opening up the primary cabinet safely, checking the nameplates on the CTs, and even to the extent of doing a little thermal scan. That's impressive. It's a little small thermal camera. Years ago, they were very expensive. Now, they're not so much. You can even get little apps, I think, that go on your phone. It's very useful to have a look for a hotspot inside that cabinet. If you see one, it may be worth reconsidering the test if you think there's an issue, and then get it fully tested before you do it. Safety is the prime concern. So the types of testing that we're doing on a transformer rated site will incorporate much, much more than meter accuracy, as you can see. There's a whole list of things which we'll go through fairly quickly for you, but we'll go through these, give you some idea of the sort of reasons why we do this and why it's important. But metering accuracy is the key component, but it's not the only component. So doing a meter accuracy test, we want to be able to pick up the pulse, and that's a prime concern. And this is courtesy of APS. I did a test with them not too long ago. We're using IR pulse detection from the front of that. This particular case, this is a Form 9 meter. So we're picking it up from the front, and you can see the indications on the screen. So there's a lot of good information that's available for you there. The meter technicians generally have their routine. They know what to look for. But the meter connections from the field test to the meter itself, typically on an IR pulse detector. We also have pulse detectors that not only pick up on the front there from the magnetic ones, we have ones which we actually have designed specifically for any pulses that come out the top of the meter through a light pipe that might run down the back of the meter base itself. And we can also share information on that one too. It's very specifically for that type of particular meter. Pulse align if necessary. You don't always have to do that, but it's a really interesting way to actually do a pulse alignment on it, which is a very useful feature before you're running a test. So I've magnified this one a little bit. It's not brilliantly in focus, but you can get the idea. And you can see on the front of this meter pickup, we have a power indication. So immediately that is connected on there. That will be a green light to let you know you've got power. And if a pulse is picked up, that little red LED will light up. It's extremely useful. Because if you don't have anything like this, you really don't know whether the meter is picking the pulse up. You have to wait and see. So this is a very good check before you even do a meter test. Okay, so we're going to use one of the screens that we get from the instrument that we use. And this is going to give us, in this particular case, a manual meter test. So the real basics are, the form factor is already set up with a site ID and a username and a site name and some really basic information. You can put a lot of information into this particular setup, or you can keep it fairly simple. It really is really up to the choice of the user. In this case, we have a Form 9S. Excuse me, a Form 9S, we have the constant. We have the meter constant entered in there already, 1.8 kH. We have the service type, serial number if necessary can go in there, and a whole range of others. We decide on how many pulses per rev we want to set this up for, and the test amps itself. On the left-hand side here, you can see the test loads under what we're going to actually select. In this case, we're going to do just a customer load that we mentioned before, although I will use this same screen a little later on to show you the full load, light load, and power factor. There are different test types you can run. Majority of the times it would be accuracy, but there are timed runs sometimes. There are timed registrations, maybe a 5-minute demand or 15-minute demand test could be required. These are all options that you have when you do your procedural testing. You choose exactly how many pulses. In this case, with one. You choose a weighted average. Because it's one, there wouldn't be a weighted average, but it's useful if you decide to do maybe 8 pulses, 10 pulses. That will really be determined by how much load is on that meter and how fast it may be rotating, or not rotating in today's world, but how many revolutions, how many pulses are we likely to see. It can take some time, so it's a decision really at the time when you set this up. One pulse would give you the answer. There's no doubt about it. You should have the accuracy you need with one pulse. Connect everything up, connect the pulses, check them if necessary, and hit the start button. When we hit the start button, we run a test. When the test is complete, which takes a very short time, with one pulse with a meter, it could be less than 20 seconds or so. It just depends on how fast, let's say, the meter is rotating around when it gets its pulses. And what we're looking at is really just the meter test results. And the prime one is this first test result here, which is the classification of the tag is going to be the customer load accuracy test. It's telling us we have 1.798 watt hours. We set it up to read 1.8 for one pulse. So that's our accuracy test. The error is very small. The registration is 100.11 and it's passed. The other two columns or the other two rows underneath are just the average weighted and an average. And you can see the two indications there. But essentially, it's that first point there is a pass condition. If you're satisfied with that, you can just hit save and save the results. The other grayed out screens here will be filled in with options to maybe redo the test. But if you're happy with that, you hit save. Excuse me. And so that's really a customer load test from a meter standpoint. So let's move on a little bit to doing our CT ratio test. And what we have now is a CT ratio test with burden. This is a typical setup. In this particular type of condition, we have the meter in the separated column at the top of this panel, and then a separate panel which opens up the primary cabinet, which is, we can see our 3 CTs in there. There's our buzz bars, there's A, B, and C. There's our test switch, and there's the wraparound flexible probes where we pick up the current flowing through that CT. So that's really what we're doing here. We're accurately measuring the current flowing through the CT. That's important because the CT is telling the meter it's one value. We're verifying that it is indeed that value. In this case, I had them double wrapped because a single wrap on these put the CT a little bit, put the flex probe a little wider than I would have liked. And we have options to tell the instrument that it is wrapped twice because you're reading twice the amount of current. This does offer a real good advantage if you have the situation that I mentioned before, where you have a very low load condition. Now it's difficult to take a measurement. If you have a 400 to 5 CT and you've only got 10 amps going through it, that's particularly low. You might be able to read it, but it might take a while. By double wrapping, you now get, instead of 10 amps, you might get 20. So you're pushing the amperage up a little bit, gives you a better chance of getting the test result. So it's a great feature to have. Now, we talked a little bit before about some of the basics of the field testing and verification. One of the things I mentioned was the nameplate. This is just one example, no particular allegiance with Alstom, just happens to be one that we picked. And you can see there's a whole range of parameters on here. But the reason that's on there is because one of the key components on there is a burden specification. These are tested in the factory when they're shipped to you, the user, and they'll give you parameters and specifications such as 0.3% in this case, it's accuracy, at a burden of 0.1 ohms, 0.2 or 0.5. So it's multi-range. So there should be less than 0.3% change in the secondary when you read it from the initial 0 burden reading when up to half an ohm is applied. So to look at that in a little bit more detail, we'll move forward to how we do that, and I'll show you some of the measurements we took on this one. But here is a typical example of a test that we did. And you can see on the left-hand side, there's a little screenshot of what we actually received as the test results. Now remember, burden's going to be present no matter what. We just described a setup where you saw where the cabling between the meter itself, the meter socket, and the CTs was very short. That's not always the case. There are sometimes cabinets which could be 20, 30, 40, 50 feet away. They don't want that. They want to design them as close as possible, but sometimes circumstances prevent that. So now they have to take into account a whole set of wiring, both to and from the CT. So that's a lot of wiring, and wiring is resistive, and therefore it has a burden. But this particular test here, you can see here, we did a little run where we can see initially at 0. If you look on the left-hand side, you'll see there's a 0 column, and then each of these is a step up to the ohmic value that we injected into the secondary loop by using our duckbill connectors inside this test switch. So we exposed the CT, if you like, to increased burden, and we're checking the accuracy is okay, even with that burden on it. And you can see it steps up and steps up and steps up. It will degrade in accuracy, it's meant to, but it's operationally, is it within the specification? And if it is, then we're okay. In some cases, you might get it in a failed condition. So that means it's investigation. You need to do a little bit more testing on it. But these are just the columns of the A phase, the B phase, and the C phase. So it seems a lot going on, but it's fairly simple to do this test. Okay, so we talked before about the 0.3% accuracy rating. There it is. This is a quick little diagram, if you like, or graphic for you. And on the right-hand side, a quick explanation of some of the math that's taking place here. So we mentioned 0.3% of those burden ratings. So 0.3%, say at 5 amps, would give us 0.015 amps of error, if you like, or variation. So if you deduct that from the 5, you're looking at 4.985, would still meet that specification. And if we look down on the burdens that we have on the graph here, we printed them out. You can see at 0.5, it's 0.9900. So it's just above that level. You can see, though, what does happen as it starts to increase. And even with a fairly sizable burden on this, you're still getting some good results until you hit 4 and 8 amps, and it drops off very quickly. I certainly wouldn't recommend hitting it with 8 amps to begin with, but make sure you look at that nameplate and see what this is telling you the accuracy is. Then you'll know what to set up with the instrument. Just a quick overview of what we just described with the calculation of the ratio, and obviously we're ensuring that that ratio is correct within there. Okay, so another example of what we can display when we do this type of testing is the ratio itself under those burden conditions. And you can see here, we have a little breakout. In fact, I'll make it a little bit bigger for you. This one is 399,626 at 0 burden, and you can see they're pretty accurate right there. And again, it depends on the accuracy levels that your company is deciding you want. Maybe it's up 5%, down 5%, up 10, minus 10, 2. It doesn't matter. It just depends on what it is you're specifying. And also check with your classifications that you're checking against. But you can see here, even with added burdens, we're still getting a pretty good accuracy. So this is a pretty good test. And you can see the little clusters that we have on the right-hand side inside that parallelogram are based around the 2 zeros, which is the 0 ratio error and the 0 phase error. So as those two values become evident to us, we can plot it. And we can plot it over each dependent burden. So the only thing changing in this case is the burden, which increases them. So it's a very good, accurate, reliable, repeatable test. Another way we can display is also with burden with an accuracy class. Same type of thing we said before. We're just showing you a slightly different way of actually doing that. So all of these values, once we have this data captured, we can display it in lots of different ways. So it really means it's a one-time test that you do, and you gather an awful lot of information, tremendous amount of information that allows you to supply that to your customers, supply it to your engineering departments, your analysts, and they can look and see perform how these are performing within the field. This one is another one I just shown just to give you an idea of what else we can do, which is a ratio correction factor, which is something that's also usually on the nameplate. And this is just giving you the ability to put in a correction if it's necessary. In most cases, even with 0 burden, you can see it's almost 1. But you do get variations, which is why we do these tests.
Hey, John.
Okay. Sorry, go ahead.
How often would you do these CT tests?
Well, it's a good question. It really is dependent upon your service. It depends how many customers you might have out there. For the most part, we're talking here of transformer-rated customers. A large utility may have tens, even hundreds of thousands of these customers. A small utility may have a few hundred. I, in my experience, would use the billing department and use the decision-making based on customer size, based on sensitivity maybe, and try do an annual test if it's possible. This type of equipment allows you to do that. And if you can't, then maybe have a 2-year, 3-year, or even a 5-year program. And you rotate around these customers and you spread it out a little bit. You know, the top 10% of your transformer-rated customers would be my first suggestion, because that top 10% is probably making up over 50% of the revenue of your company. So it's an important place to start, and then you can gradually work your way around to the others. But it's a good question, yes. So it really is variable.
We actually have another question also, John. Sure. What is a typical frequency of CT, PT testing at a particular site over time? How often are utilities visiting a site? You kind of answered that, but... Yeah. It's
related to the same thing. The frequency really will depend on how many staff, the training, depends on the customer. And I think it's really based on the customer sensitivity to a certain extent. If you have a very large customer, I live in Arizona here. One of the customers I did a test on this was Intel. It's a sizable organization. It's huge, and they're very sensitive, and so they want to do tests regularly. So they're an exception. So it really does vary. I would say you need to visit that customer. Anyone with CT-rated situations like this, I would say at least once a year. You just need to try and do a quick test. When you get familiar with this equipment, you can set this up and run a test. It takes no longer than about 30 minutes to run this test. It's not a race. I'm not suggesting it is, but that's important to know that it's not a long-term half-day test. It can be done very quickly. You can put the instrument back in, close the lid, put the instrument back in the truck, run to the next site. It's all run on batteries. So it's a very quick test, but there are good questions, and there is no right or wrong answer to that. But I would say at least once a year, it would be my goal.
Okay, thanks, John.
Okay, so phantom load testing. This idea, of course, is now to control delivery of the load as opposed to the customer's load. And you can see here, it's difficult to get a clear photograph because I don't want to get too close. But what I'm showing you here really is the connections with this little red easy clip. These are also on the actual current on the test switch, current on the test switch, current on the test switch. And you can see down here, the duckbill is in place. So what we're doing is we're driving current into this duckbill. It then comes in the bottom here and comes around this cable and goes into the top. So we are bypassing the CT and we're going directly into the meter under a control condition, typically 2.5 amps. There's our test switches that we use. These are very familiar to most people, I'm sure. We don't need to go through a lot of detail, but suffice to say, you can clearly get access to these through the cover and the cover off. This is the one where that's a shorting switch, that's your shunt. So if you operate this and it comes down this way as you open it, that basically shorts out the CT, opens it up. So you've shunted the CT out. So there's no current coming to the meter, but it's still operating. And this other feature here is the duckbill connection, which is your test jack. So if you drop that one all the way down, then you can put your duckbill in there and safely run the test. These are really extremely useful, and they're pretty much everywhere we see now. So you can connect everything you need to connect through the test switch. This is the same screen we saw before. The only difference is you'd have full load, light load, and power factor selected. You choose what you want: full load, light load, and power factor. And I would say, for the most part, you'd be looking at a full load, maybe 4 or 5 pulses, perhaps. Light load, because the light load is now 10% of the 2.5 amps. It's a very low condition. You may only want 1, 2, possibly 3. When you go to do the power factor, you now have full load again, which is 2.5, but now your power factor has changed to 0.5. So again, it might be 1, 2, or 3. So you can vary this around, but when you do that test, hit start, this is the sort of screen that you'll receive. And you can see here, there are 2 examples. In this case, on this sequence we did, we can see a full load accuracy, we can see a light load accuracy, and we can see a power factor. And that was done with 1 pulse. So it's pretty impressive with 1 pulse. Not always easy to do it with 1 pulse. Sometimes it might take a little longer, but if you get the accuracy you need with 1, you don't really need to do 10. So it's a question of doing a very quick test on that. So I want to just have a quick break and hand over to Tom, if Tom's there. Are you there, Tom? Is Tom available? Andy? Hello, Andy.
Hold on. Tom's here.
Okay.
He just has to unmute. We're just figuring that out.
Okay.
Okay.
Tom, yeah, hello, Tom?
Yep, I'm here.
Hi, Tom. Sorry, I just wanted to introduce you to the group. Just talked about doing a few slides, if you wouldn't mind, just to introduce yourself and go through the demagnetization and the admittance.
Sure. Okay. And you have the slides, right, John?
Yep, right there.
All right. All right. So one of the things about your field testing is you do want, or even shop testing, because we see this problem in the shop as well, is that you can have magnetized CTs. And the problem with the magnetized CTs is that they are going to show a fairly large error at times. It's very easy to demagnetize a CT, and basically what you do is you put it into saturation, and then you gradually reduce as you're stepping on down through. Now, some field equipment, the shop equipment is very, very good at doing this. Sometimes in the field you have to do it more than one time to actually get the unit demagnetized. But often, if you see bad results on a CT and the CT is not obviously damaged, very often the bad results are actually just the result of magnetized CTs. So it is something that should always be done. It's always a best practice to do it anytime you are working with CTs, whether it is in the field or in the shop. You should always demagnetize them at the end of the test. We have seen brand new transformers directly shipped from the manufacturer be magnetized. So you cannot just assume that because you're getting them brand new that they are good to go. You've reviewed the test data from the manufacturer and everything is fine. It is possible that those CTs may arrive at your facility magnetized. So again, always the best practice.
Okay.
Go ahead, John. You want to jump on to the so admittance testing is a really interesting test. I know that it is very popular in certain parts of the country and not nearly as popular in other parts of the country. And some of you have maybe never even heard of it. It is admittance is measured in millisiemens. It tells you basically how easy a circuit allows current to flow. But really think of it as a snapshot. One of the best practices that you do when you go out, especially again to your transformer rated services, you open up this big old cabinet and what do you see? You see stuff. Well, if the guy who was there before you, if John Carroll was out a year before or 2 years before and he took a picture and put that in the file, whether it's an electronic file or whether it's a paper file, it doesn't really matter. I've seen at some utilities, they used to take the old Polaroids and those would always be stuffed into the file. If I have that picture, if I pull it up on my tablet and when I open up that cabinet, it looks a lot like my picture, I feel pretty good. I feel pretty good because I'm probably at the right site. Because sometimes you can have locations that have a dozen or 18 different metering sites there. And are you at site number 5 or site number 6? So opening up the cabinet and seeing exactly what's in the picture helps you feel comfortable that A, I'm at the right place, and B, nobody's been screwing around with it because it looks the same as when John Carroll was out here 2 years ago. Admittance is very much the same thing. An admittance test all by itself means nothing. Okay. However, if John Carroll did an admittance test 2 years ago and I come out and I do an admittance test and we get the same result, I can feel really good that nothing has changed in that circuit. And that means an electrician hasn't been in there messing around trying to hook up some new part of the plant or some new lighting services or whatever. There hasn't been, there's no broken wires, there's probably no loose wires, there's no additional corrosion. All of the things that, as John was talking about before, burden, all of those things can add burden to your circuit, which as we know, can dramatically, once you get over that knee, as you saw on the chart a few slides back, once you get over that knee, your accuracy drops way off. So think of an admittance test just like a picture. If John Carroll goes out, takes an admittance test, and 2 years later or a year later, I go out and get the same answer, I can be pretty comfortable that nothing has changed in that circuit. If I get a different answer, it doesn't mean that things are bad. It doesn't mean that I've got a problem. It means that something changed. And now I know that I have to look a little bit harder. What changed? Is it just a loose wire? Is it corrosion? Did somebody add something to this circuit? It could be any of those things. So again, for the guys that use admittance tests, they love it. They absolutely love it. The key now is because we all have our tablets and our laptops and things of this nature, we have access to the data from 3 months ago or 3 years ago. So we can pull up the admittance test and say, yep, this site has had, basically I'm getting the same answer as we did last year as John Carroll got 2 years ago. So I feel pretty good about it. All right, so that's kind of admittance testing in a nutshell. So the new unit, as John was talking about, does do admittance testing as well, so you don't need a separate box for doing it. Admittance testing became popular back in the early 1990s. The folks that came out with that did very well with it, and like I said, regionally, I know a lot of guys in the Midwest use it quite a bit. I've seen a couple of guys in the Northeast and a couple of guys in the Southeast use it. I'm not sure, John, how prevalent is it out on the West Coast?
There's occasions, Tom, yes, that you do come across it, but for the majority of people, they don't see the use for that. They tend to want to do the actual customer load test. I mean, this is effectively a no load test, is effectively what this is performing, but it is extremely useful to do it. You're quite right.
Well, it's okay, John. Someday the West Coast may catch up to the Midwest.
They might finally figure it out.
All right, by the way,
Tom.
we lost your video, John. We lost your video.
Oh, yes. All right, sorry, I must have been there. Let me try it again. There we go.
There you go.
There we go. All right. All right, thank you, Tom. I appreciate that.
No problem.
Thank you, sir. Okay, we got about maybe 10 minutes, maybe less than that. So I'm just going to run through really quickly one final aspect of a full site test, which has become much more relevant these days than it used to be, and that is harmonics. You're all probably familiar with what harmonics are to a certain degree. They are integer frequencies. We can go into some of the fast Fourier transform calculations and algorithms, but we're not going to do that. What we really want to know is what's the effect of this. But the essential thing to take away from this is, you can see here, there's just a couple of slides I put together, one of which is the harmonics on the voltage side. This is A phase on the top left there. And on the bottom, we've got harmonics on B, just as another example. But you can have it on A, of course, and it's the same phase. The important part about this is the amplitude on the left-hand side here, as you can see, is in percentage. That's percentage of the actual fundamental. We don't have the fundamental in here because otherwise it would have swamped this completely. So the important part about this is, what is the effect? Harmonics are just around us all the time. They are a natural phenomenon that's almost created by load conditions and different types of loads. I'll talk a little bit about that in a second. But the takeaway I would give you from this is, overall, without going through a whole algorithm chart here, you can see there is a sinusoidal component to this. If you look at the harmonic index on the top left one, on the amplitude there, you'll see you've got the second harmonic is that little one on the bottom there. Then you've got the third, 4, 5, 6, 7, and so on. The majority of times in the world that we are, which is an inductive world, we will get these harmonic conditions, third, fifth, seventh, ninth, 11th, and so on. These are the most dominant. These are the most significant harmonics that you'll see, and they're everywhere we are. We have them. So there's a lot of different things that are going on, but this is the important part, and you can see it tails off, and then it actually comes back a little bit, and then tails off and comes back on again. So this is very significant, the way it looks, and that's a signature, if you like. Harmonic distortion. Total harmonic distortion is the value of all of it together. And in an ideal world, it should be less than 5% on the voltage. This is not a harmonics presentation. We may do another one of those later on, maybe in more detail. But essentially, these are the ways we can actually look at these. And to illustrate that perhaps in a better way for you, this is a snapshot I took of one of the screens I did recently, which I thought was a very interesting situation. The customer was actually a semiconductor manufacturing operation, and they use a significant amount, excuse me, a significant amount of switching conditions. And so what you'll see here is, you'll see, in this case, the voltage, excuse me, so I'm going to throw too much talking here. So the voltage here, you can see, is the red phase. And then underneath that, you'll see the red dotted line, which is your current going through the same way. The interesting part about this is the current actually is leading the voltage. It's not completely unusual, but it's certainly less rare than the other way, which is lagging. So that's due to the types of loads that they have in that building. All of this, the important of all of this is, how does it affect us? So the question I'm going to finish with, to a certain extent, on this is, what's the problem with harmonics? Well, the number one problem with harmonics is illustrated by that picture right there. And you may have already figured out that the real big problem with this is heat. And these types of harmonics don't propagate down a cable in the center core of the cable. It's not designed that way. So they have what they call skin effect. So it kind of spins around the cable and creates a hot cable. In rare cases, it can get excessively heated, and you can get overheating transformers. You can obviously get loss of service, and there's a safety hazard, big one. But one of the issues too is, how does it affect a modern day meter? Well, the AMI mesh itself is a frequency domain mesh. Because this is a frequency domain as well, you can get interference. Not necessarily to prevent the instrument from working, but the meter itself may be interrupted with its mesh, which means it may not be able to report. And then it creates a reporting problem. So having an instrument that at least can give you and identify what you have is really key. And this is a particularly good feature that we put together in this machine. Can we reduce harmonics? Well, not completely. It's very difficult to eliminate them. We live in a non-linear world where they're everywhere. I've given you a couple of examples without going into a lot of detail with pulse width modulation conversion and AC frequency drives, very common around the world, and pumps and drives. Everything's driving towards efficiency, which means dropping the watts down. Like, look at the light bulbs that we have in today's world. They're a fraction of watts compared to a 100-watt incandescent bulb, but they don't drive it sinusoidally, so there's consequences. Thousands and thousands of products in your home, and everywhere we go has got switch mode power supply devices, and this is the sort of typical screen that you will see. So, without going into any more detail on that, these are just some of the impact conditions. How can we reduce them? Well, rather than eliminate them, like we said, you can measure and determine what they are. You can assess the most significant. There's a lot of great products out there that do active filtering that will reduce the most significant. That could drop the problem down by 50% right there. And many customers out there, as you're probably aware, will do power factor correction capacitors. That's also fairly common. Be aware, though, that they do switch as well. So it's a bit of a balance between them all. And the active harmonic filtering also is now very much a part of transformers. Many of you out there might be familiar with K-factor rated transformers. They are designed from the beginning to accept a level of harmonic conditions on the circuits, which means they don't overheat. They have active filtering in there. So again, these are all ways that we can reduce the impact. It's very difficult and very expensive to try and eliminate them. And I think we can live with them up to a point, but this is a way we can actually help. And this is all part of the testing that we do in this whole site verification. So as you can see, there is a lot going on. We can discover and prevent a whole range of different conditions. We've got billing errors, which are obviously fairly immediate. We've got bad setups, detect the diversions, any kind of metering issues that we don't know about, any kind of communication issues. It also means you don't have to do unscheduled truck rolls. You could go and have a program to do a regular test every day unless there's something significant. If there is, then you can identify that as a service project. But any discrepancies that Tom mentioned too, between what was believed at the site and what you actually see is vital. And so as Tom pointed out with some of the admittance testing where you're doing a comparison of your Polaroid picture, you're doing the same thing here. The instrument could already have data in it from a year ago, and you're doing a secondary test. So it's pretty complete setup. That pretty much covers what I wanted to go through. So I really appreciate everybody spending some time with us today. There's a lot going on with this machine, a lot going on with the testing, but don't be overwhelmed by it. It's actually very simple to set up. It's very simple to do a recording. It's very effective information that we think is vital for your utilities and your metering programs. So at that point, Andy, I think I can probably hand it over to you. If there's any questions out there?
Sure thing. Thank you so much, John. And if you guys have any questions, now would be the time to kind of jot them in the little chat box there. If you don't have a chat box, and I think you can raise your hand on the in the WebEx, and we can try to unmute you if you have a question you want to ask, if that's easier. I know some people on their devices they're watching us on right now cannot actually type in the chat. So we do want to get to any questions you guys do have. So we'll give you a minute to type those in. Meanwhile, we guys want you to return next week where we will be doing electric vehicle trends. We'll dive into the EV trends in the industry and how to properly calibrate those commercial chargers. And then the following week, we'll have streetlights and 5G metering, learn how those communication devices are being metered on smart poles and how you can utilize those streetlights to maximize revenue for your utility. Both really, really good presentations coming up, and we are looking for your ideas, what you would like to see for our next session coming up next month, being January already. I can't believe today is December 1st. So we are looking into next year already, and we will be sending an email out right after this session to get you guys to do maybe a little survey, get us some ideas for our next session, what you guys want to see. And, you know, we hope you will continue to join us for these sessions next year. And if you guys have any questions, please jot them down in the chat. You can always find us online. John had his email on the slide before. You can always find us at tescometering.com/TESCO-Tuesdays. All of our information to sign up for those will be on there, including the next session once we post those. And if you guys need a copy of the presentation, it will be on there. Our video usually takes about a day to download. We'll post it next week. If you missed any of our presentations from previous weeks, they are on the website as well. So if you guys have any other questions, I don't see any hands raised. We'll let you guys cut out early unless John or Tom, you guys have anything else to add?
No, thank you, Andy, for setting it up, and thanks everybody for spending part of your day. And just for everyone to know, Andy's just been talking there. That's actually Andy holding our new recruit in our PPE equipment. So nice job, Andy.
Yes, I got to be a meter tech for a day.
Right?
It was fun. All right, guys, thank you so much for joining us. We look forward to seeing you next week, and have a fantastic week, everyone. Take care. Thank you.
Thank you again.